In this video, we are going to discuss about normalized least mean square or NLMS algorithm. I hope you have gone through my previous videos on least mean square algorithm. There we have discussed in detail how to derive the LMS algorithm and some analysis of LMS algorithm we have also covered. Now in this video, we will come to NLMS algorithm. Before that, we'll discuss very briefly what is LMS algorithm and what are the difficulties in LMS algorithm so that we can go for NLMS algorithm. Okay, and what is the meaning of this normalized version of LMS algorithm. So in LMS algorithm, you have seen that we had considered one unknown system W0, and if we apply input sequence xn is the input sequence, and corresponding output will be taking convolution between this W0 and xn. We will also consider observation noise or system noise, and that is the Vn. This is random, and this output, this is the desired sequence Dn. So this xn and dn, these two are available. Our objective is to estimate this unknown coefficient w vector, w0 vector. So to do these things, what we'll consider same input sequence xn. So this is your xn input sequence. It is coming here, and we'll consider one FIR filter, and that coefficient is wn. Okay, we'll tune these things. And this output is yn, suppose. Now we'll compare these two. So this is plus, this is minus, and this is the error en, and based on this error, we'll tune this wn vector to get better estimate of w0. This was the objective. And for LMS algorithm, so what are the cost function we have considered? For LMS or least mean square algorithm, we started with one cost function jn. At nth iteration, the cost function is half square n. Instantaneous error squared, that will try to minimize in every iteration. Okay, and if we consider this one based on gradient descent approach, we have got one update rule for this wn. So and that wn we have got for LMS algorithm, wn plus 1 is updated from wn with one correction term, and that correction term is mu, that is step size, times this en and xn regressor vector. Okay, what is xn regressor vector? That we have already discussed. So this is nothing but the current input sequence xn and previous xn minus 1, xn minus 2, like that up to xn minus l plus 1. So if I consider it's a l, the filter length is l. Okay, so this is the regressor vector xn, and this one is the corresponding correction term that is added with previous wn, and we will be getting a new wn plus 1. That is a very simple LMS algorithm or least mean square algorithm. Now here the main difficulties. So what are the issues with this LMS algorithm? So main concern here is that this correction term. So first concern is this thing, that this correction term is proportional to this xn regressor vector. So what is happening when, so xn, this correction term is proportional to xn regressor vector. So when xn vector is large, okay, then obviously you are expecting a large update in wn plus 1. So wn plus 1 is updated sufficiently. So that is not a huge problem, because we can update, we wish to update wn based on this gradient. Okay, but this mu we need to choose proper way, then only this algorithm will converge, otherwise it may not converge. Okay, so if xn is large, then what is happening? This wn will update largely. Okay, but it may introduce some gradient noise. All the taps may not go towards proper directions. That we'll discuss later on. So this is not an issue. But when this xn vector is low, okay, then wn, there is a negligible update because this correction factor is very small. Whatever mu is there, if xn vector is itself, it's low, very low, then obviously we can expect that the update in wn is very little. So it is a negligible update. And that is the concern. So whenever there is a xn is very low, that time there is a very little update, but you want sufficient update for that, even though xn is low. Then what we should do? Okay, that is one concern. And second one is that the step size, this step size mu. So mu we need to set it properly, otherwise it may not converge. So what is the bound for this mu? The mu, it should be within 0 and 2 upon lambda max. What is the lambda? Lambda is nothing but eigenvalues of this autocorrelation matrix R. So R, you know that R equals to expected value of xn and x transpose n. Okay, so this column and this row vector, you will get a matrix, and its expected value will give you the autocorrelation matrix R, and the eigenvalues of autocorrelation matrix, that is the lambda, and maximum value of this one lambda is lambda max. So this mu should be bounded within this one. It should be less than 2 upon lambda max. So it clearly says that this mu depends on, so what is the meaning? Mu depends on this input statistics. That is the important thing. So if input is different, the lambda will be different, and that time you need to adjust the mu proper way. Otherwise, algorithm may not converge it. Okay, so that is a great difficulty. So how to avoid these two? Okay, so first one is that when xn is very low, xn regress vector, the update is very little, negligible update. And second concern is that if mu is not set properly, then algorithm may diverge. It should be less than 2 upon lambda max. So lambda max depends on the input statistics. That thus this mu, to set the mu, you should have proper knowledge on input statistics. Okay. Now in LMS algorithm, we'll see that this mu does not depend on input. Okay, that we can rectify. It's a constant. It's up to 0 to 2 only. So NLMS algorithm will converge between 0 to 2. That is one thing. And if xn is low, then also there is sufficient update in NLMS algorithm. So what we will do in NLMS algorithm? Okay. So we will discuss NLMS algorithm. Now here the cost function, how to check the cost function. So we can do in different way. So first one, I'll suggest that. So from this wn, we used to get wn plus 1 for this NLMS algorithm. So this NLMS algorithm will try to find this wn plus 1 considering this optimization problem. What is that? We'll start from, suppose I have current position wn. So I'll look at one vector w which is closest to this wn. That means w minus wn, it's norm 2 square. This value is minimized. We'll try to minimize this objective function, one w, one unknown value w, which is closest to wn. That means the difference vector is very small. That will try to minimize. So I'll call it argument minimum. Okay, for this w. So which W will give you these things, and subject to one condition. So one condition will put that we want to make current error 0. So what is the meaning? The current data is dn, so desired sequence is dn, and so I will consider this weight w. So this weight w will produce the output w transpose into xn vector. So this is the corresponding output at w at n iteration, n plus iteration, okay, for these w vectors. So this one should be 0. It should not give you any error. So I want one such w which will make current error 0 and which is also closest to my previous update wn. So this methodology is called minimum disturbance. We don't want to disturb the current position greatly. Even we want to get one solution which will make the current error 0. Remember that we can have infinite number of solutions. So these things. So we can have infinite number of solutions for W which can make output 0, current error 0. Because I have only one equations and we have L number of unknowns. We can set L number of unknowns in different way to make current error 0. But one condition is that weight should be very close to Wn. Okay. So this is the formulation for normalized least mean square algorithm. Now how to get this Wn plus 1, update for Wn plus 1. Now this is one constraint optimization problem, because we have one constraint. This is one constraint, dn minus w transpose xn, that is equals to 0, and we want to minimize this norm 2 square. Okay. Now to tackle this one, we'll use Lagrange multiplier. So considering Lagrange multiplier, okay, this is important concept. Multiplier lambda, that will include, so I'll consider one cost function at jth iteration, nth iteration, okay, jn suppose I am calling it. So that is this cost, original cost, that is w minus w n plus 1, n, that norm square. This will try to minimize, and this is the constant, and that constant will add with one Lagrange multiplier lambda, and it is dn minus w transpose xn. Okay. So this is one cost function considering the constraint as well as main objective functions. So this is the overall cost function that we have considered. Now we will try to minimize this cost. Okay. So to minimize this one, what we will do? We will try to consider the gradient of this one, del j del w vector. Okay. So the gradient of this one, you can see these things. This is the cost functions. So derivative of this one will be 2 times of w minus wn. Is it okay? So first term is coming at considering 2 times, this is w minus the previous update. This is the derivative of first term, and second term it is a lambda. This is a constant, and this constant is derivative is 0, and this is considered with respect to w. So I will be getting only xn. Okay. So lambda minus an xn, that term is there. Okay. So what we will get? Minus lambda times xn vector. And so for if I consider wn plus 1, one could be one solutions. Okay. Then obviously that wn plus 1 should make this thing equal to 0, because gradient should be 0 for optimal solutions. So if I consider that wn plus 1 is the optimal solutions, I am considering that wn plus 1 is my optimal solutions, then obviously 2 into I replace w by wn plus 1 minus wn and minus lambda xn vector, and that should give you a null vector. This is for optimal conditions. So gradient, this gradient should be 0 vector at optimal conditions. Okay. So now from here we can find out first this wn plus 1. Okay. So how to calculate these things? So these two I can wn plus 1 minus wn. Okay. That should be equals to lambda by 2 into xn. Right. Now from here we can extract this one, wn plus 1. It should be wn plus lambda by 2 xn. So you can see that it is also very similar form that with previous update was there wn and one correction term. But here difficulty is that this lambda, still lambda is unknown to us. So we need to find out what is the corresponding lambda. Right. Now what I can do, this wn plus 1, we have already said that our solution should satisfy or should produce the current error 0. So our current error is these things, dn minus w transpose xn. So w is replaced by wn plus 1, then wn plus 1 transpose xn, that should give you 0. No? So that is the one condition. So that condition again we will choose to find out this value of lambda. So we have got this one, this form. So what is the condition? Condition is that, so this dn minus w transpose n plus 1 times xn, that should be equals to 0. Okay. Now here we can replace these things. So it is dn wn plus 1. Now I replace this one by wn plus lambda times xn vector. Its transpose, okay, and it is xn, and that is equals to 0. Right. Now if I simplify it further, it's a dn. Now this, if I break this one, so w transpose n times xn, and it is minus lambda x transpose and again xn, and that is equals to 0. Now can you look at this one? What is this? dn minus, so this part is nothing but this one, I can consider that. So this is nothing but your yn, because output dow transpose into xn. At nth iteration, this is my filter coefficient, this is a regressor vector, and this one, this is wn, this is the xn regressor vector, yn, this yn is nothing but w transpose n and xn vector. This thing we have discussed in detail in my previous videos. If you have certain doubt, please go through that one. Okay. So this is my current output, and dn minus output is nothing but en. So basically it is en. So this term is nothing but dn minus yn is en. So we can replace this one by, it is a en, it is a minus lambda, it is x transpose, it is xn, and that is equals to 0. Okay. Now remember, this is a scalar quantity. Why? This is scalar, because x is a column vector, xn is a column vector. So if I take x transpose, so x transpose n and xn, this is one row vector followed by a column vector, same dimensions. So you will be getting a scalar quantity, and this is also we can write in this norm square, xn norm 2 square. This is nothing but norm 2 square of this one. Okay. So that also we can write out. Right. So then what is the lambda? Lambda is nothing but en upon, so these things is nothing but norm xn, that 2 square. So this is my lambda. That lambda we can plug in here, plug in the original update equations. So what is the update equations? So already you can see that Wn plus 1 is nothing but Wn plus lambda by 2 into xn. Okay, I think we have missed the two terms here. So this was the two terms here, and here it should be by 2. Okay, so please take on correction. So this is lambda by 2. So this is lambda by 2. Okay, so this lambda by 2, actually it is like that. So I can replace total lambda by 2, not only lambda, right? So here this lambda by 2 I can replace by this factor en upon norm of xn square. So what is the update rule then? So we are getting the update for NLMS algorithm, that is Wn plus 1 equals to previous Wn plus lambda by 2 is replaced by En upon norm of xn, that square, and then we had this one only xn regressor vector. So same xn regressor vector I'll multiply here. So this is the update rule for NLMS algorithm. Now here what we can do, we can introduce the step size. So mu could be introduced here, and so after introducing this one step size, so what we will get, so this Wn plus 1 is Wn previous one. Now I can introduce one step size mu, okay, along with this one. So then En into xn vector, and denominator this term is there. Now you can see that sometimes if this vector is very small and it is close to 0, no, if it is close to 0, then its update is very large. It's becoming very large. This value is becoming large. Earlier we said that if xn, if this regressor vector is very small, then update was very little. Now you can see that we have one counterpart here. We have divided by this norms 2 square. So if this value is becoming small, this value is becoming very large. It will compensate that one. But it will be problematic if it is very small. No? If it is close to 0, then this value will become very large and it may diverge. To avoid these things, what we will do that, so to avoid the division by 0, these things, so we'll include one regularization constant. So one delta, so along with this one xn norm square, I'll put one delta, I'll call it delta n. Delta n is a regularization constant, it's a small positive value. So delta n is a small positive value. So typically it is, you can consider 0.001, okay. Just it is introduced just to avoid division by 0, nothing else. When this value will become 0, this value will become, right term will become infinite. So you are going to get absurd results. Okay, huge update, huge change, not update. That is not desired one. So to avoid these things, we will include one regularization constant, lambda n or delta n. Okay, and mu is the step size. This is your step size, and that is used to control or to get some trade-off between convergence rate and steady state error. If you know that if mu is very low, then once it will converge, it will produce very little undulation, mean square deviations. Means steady state error is good if mu is low, but when mu is large, then steady state error is poor because it will fluctuate a lot at steady state. But one advantage is that because of this, it can converge very quickly. Okay, so in NLMS algorithm, we can show that this step size mu, okay, will converge within one condition, that mu is within 0 and 2. So you can see that this algorithm will converge within steps for the step size from 0 to 2 safely, and for that no need to use any input statistics knowledge. Okay, it is independent of input xn. It is not depending on autocorrelation matrix, lambda, or all those things. Nothing is there. So we can improve the performance of LMS algorithm using NLMS algorithm, and this is the update rule for NLMS algorithm. So this one. Okay, so with respect to LMS algorithm, this is the introductions. This part, norm of xn square plus lambda n, delta n. Is it okay? Now we'll try to give you some physical interpretations or graphical interpretations, how it will converge. Okay, how it will converge, that is different things. So some graphical interpretation we will try to give you, and it is basically projection point of view. So whatever you have formulation we have considered, that we can think of a orthogonal projection kind of things. So why it is so? Okay, so can you see these things? So first we have said that we will get Wn plus 1 from one argument minimum of which one? I'll choose one W which is closest to Wn. Okay, so that W we are looking for, and subject to the condition that the current error is 0. Okay, means Dn minus W transpose Xn, that will give you 0. And this one, this is your condition, it's constraint, and that is nothing but one hyperplane. Because I have one equations containing L unknowns, and their combinations will give you this Dn. So this will give you some sort of hyperplane, and if there is no noise, Bn is not there, then obviously on this hyperplane our optimum solutions is also there, W0 is also there. Okay, so it will contain the optimal solutions if Vn is absent. So if I consider that Vn is not there, so then this will give you some hyperplane, one plane we can consider in the L dimensional hyperplane. So I can show in this way. I can consider this is one hyperplane. Okay, and this hyperplane I will call it Hn at nth iteration, Hn. So this is my Hn hyperplane, and suppose, so what we are looking for, so our solution W should be on this plane, because then only this current error will become 0. But I can choose any point on this plane, but which point? I have infinite possibilities, infinite way we can choose the W. Okay, now suppose my current point is here, so this is the Wn vector. Okay, so what the first equation is showing that, so I need to choose one point on this plane. Okay, suppose if I choose this point here, this is my point W vector, then the distance between W and Wn, this distance will be minimized. Okay, so when it will be? If it's orthogonally projected on this plane. Suppose if I choose a point here, if I choose a point here, W vector, obviously the distance is larger. So that distance will be smallest one. So this argument minimum, this one, it's a minimum, this is a distance only, W minus Wn, that num2 square is nothing but L2 distance. That L2 distance is minimized, meaning is that if I take a orthogonal projection on this plane from this point Wn, that will be giving you Wn plus 1. So it is basically orthogonal projections from Wn. Okay, so whatever we are getting, this update equation Wn plus 1 is nothing but Wn plus this En times Xn regressor vector and norm Xn square, that is actually it's giving you this point, and that point is on this plane, and then this time this distance is minimized. Basically we are taking orthogonal projection on this hyperplane. So that is the concept of NLMS algorithm. Okay, I hope you have got this point. We will discuss more about the NLMS algorithm, how it will converge, and why mu is bounded between 0 to 2. Okay, what is the logic behind that? Everything will be discussed in the next video. So keep watching. Okay, thank you.